with a presentation from our experts and then open it up for questions. You can ask your questions by typing them in the comments section of your webinar platform. We may not get to all of them, but we will do our best. As a gentle reminder, by being here, you're agreeing to abide by NVIDIA's code of conduct. Please be kind and respectful to each other and to our panelists. With that, we're going to start off with introductions. My name is Katrina Reel. I'm a Principal Technical Product Manager on the running the Cuda Education program at NVIDIA, and I'll be acting as one of the moderators throughout the event. And now I'm going to pass it over to Jin Sung, who will kick off introductions for our panel.
Hi, everyone. So my name is Jin Sung Kim. I'm from the quantum computing team at NVIDIA. I'm a developer relations manager. I'm joined with several of my colleagues here. Let's just go around in a circle, and I'll hand it off to my colleagues to introduce themselves. Monica, would you like to say a few words about yourself?
Sure. I'm Monica Van Dier, and I'm a senior technical marketing engineer in the quantum group at NVIDIA, and I lead the Cuda Quantum Academic Initiative. Pass it on to Mark.
Everyone, my name is Mark Wolf. I'm also a technical marketing engineer on the quantum team, working on Cuda Q Academic and some of the other initiatives we have. Pooja, do you want to go next?
Hi, everybody. I'm Pooja Rao. I'm a quantum algorithm engineer at NVIDIA. I work at the intersection of quantum computing and high performance computing. More recently, I've been working on using AI techniques for quantum computing. Really looking forward to this webinar. And Mike, if you want to go ahead.
Hi, everyone. I'm Mike O'Keefe. I'm a senior solutions architect on the higher ed and research team. We help researchers reduce time to results through accelerated computing solutions, and quantum computing is one of the areas I focus on. Jin, back to you.
Did we get Efrat?
Oh, sorry.
Hi, everyone. My name is Efrat Shabtai, and I'm a senior product manager at NVIDIA. I'm the product manager for Cuda Q that we'll talk about today. So really looking forward to your questions in this presentation. Back to you, Jin Sung.
Great, thanks. So I'll show a couple of slides on our overall platform. Zach, would you mind pulling up my slides? Thank you. Yeah, so let me go ahead and tell you about some of the work that we've been doing in the quantum space and really the work that we've been doing with the entire quantum ecosystem. So first of all, we're not building our own quantum processor. There's plenty of people out there who are very, very good at that already. But what we are very good at and have a lot of experience in is building heterogeneous compute systems with new types of accelerators, networking them together, scaling them out, and making them into useful scientific tools. So what we think this will look like in the future will be a quantum computer of various modalities next to a supercomputer. So quantum computers are not going to do everything themselves, but will be a critical part of solving important problems that we can't solve today. And on the flip side, GPU supercomputers are very useful tools for making advancements in quantum computing today. And we think will be an important part of useful workloads with a quantum computer in the future. So what we have to do is carefully consider a fully integrated system, both from the low-level systems integrations to the high-level methods for developing applications. So this vision is our North Star. We call it the accelerated quantum supercomputer. This is what we're trying to help the entire ecosystem build towards. So what this is connecting QPUs of all architectures to AI supercomputers for the purposes of developing hybrid applications, leveraging AI methods for quantum, developing the low-level and low-latency connections between a QPU and a GPU, and all the way up to the high-level libraries for enabling the end user to program the system as they would a normal computer. So as a platform company, our success is dictated by the success of our partners. So when our partners succeed, we succeed. So we're really happy and proud to be able to partner across the entire quantum ecosystem. We have a pretty amazing ability and privilege to be able to work with nearly every quantum computing company, from early stage startups to some of the largest companies in the world. So how do we get to where we are today to where we want to be in the future? To really realize this vision of the accelerated quantum supercomputer, very broadly, the three biggest challenges are to build better performing quantum hardware, better algorithms and applications to identify useful workloads, and to be able to scale out quantum error correction. So we're building out a platform that we think is going to help with each one of these things. So Cuda Q is our software platform and programming model for quantum computing. It's open source and qubit agnostic. If you're familiar with Cuda, it's the framework that has allowed the massive scale of the GPU and is the best way to program a GPU. So in a similar way, Cuda Q is our framework for programming a quantum processor, integrating them into supercomputing scale GPU systems, and ultimately making quantum successful overall. And so a big part of this is the enablement and integration with the entire ecosystem. So the logos you see here on the right are QPUs that you can access today with Cuda Q, with several more not listed here that are in the process of integrating. You'll notice that nearly every modality, qubit modality here, represented here, as well as both digital and analog quantum processors. Also highlighted here is our integration with AWS Bracket, which now hosts Cuda Q natively on their environment. So you can access all the QPUs available there through Cuda Q, as well as various GPU instances for high performance simulation. In addition to quantum hardware, we've also developed state-of-the-art tools for simulation. So for simulation, we've developed a set of libraries called cuQuantum, which are extremely performant and powerful tools for developing algorithms and applications and understanding scaling behavior. For us and our partners, simulation is a really complementary tool for quantum computing. So there's many reasons to leverage simulators. Many of our partners and users like to use them to prototype algorithms or workflows before they run them on real quantum hardware. Others like to use it to controllably study the effects of noise on an algorithm and error mitigation techniques. And even others help them use simulators to help them design and develop better control techniques or refine their parameter space for developing quantum hardware. So one thing that's important to mention here is that we release our simulation acceleration libraries independently from Cuda Q, so that every other framework within the quantum ecosystem can also pick up our acceleration capabilities. Now, on the opposite ends of the stack, we have a new set of libraries called Cuda QX. These are high-level libraries for accelerating applications development. For Cuda, libraries have been a big part of making it easy to program applications on the GPU. So the first two we've released are Cuda Q QEC for enabling quantum error correction and studies and workflows, and Cuda Q solvers, which has built-in primitives for developing quantum chemistry applications. At the very bottom of the stack, we have a system and reference architecture called DGX Quantum. This is a system we developed in collaboration with Quantum Machines, which enables a very low latency connection between a GPU system and a quantum control system. So this is the first system of its kind. It won't be the last, where we have a direct coupling from a GPU to QPU and can start exploring workflows leveraging GPUs for things like real-time calibration, control, and to start to do investigations in real-time error correction. So this is our platform. It's open source and available to use. We build the whole platform, but we distribute it in a disaggregated ways. So our partners and our users can either take the whole stack if it's useful to them, or they can pick and choose what parts of it are most useful to them. So we're also, I want to mention that this model of the accelerated quantum supercomputer is already starting to happen at various sites around the world. The ones here are already deploying quantum processors next to GPU supercomputers and really starting to push the forefront of what's possible with GPU supercomputing alongside quantum computing. So with that, let me pass it to Monica to do a couple of examples.
Yeah, thanks, Jinsung. Zach, if you wouldn't mind sharing my screen. So that was a great overview of accelerated quantum supercomputing and the Cuda Q stack. And so I want to dive into a little bit of a live demonstration to bring Cuda Q to life and give you the basics on how to get started programming with Cuda Q. So I know the audience is going to be coming from a wide variety of backgrounds. So I really do want to start, for those who've never seen the notion of a qubit before and are just here because they're interested in quantum computing, one way to follow along is to think about a qubit as a vector pointed in some direction on a three-dimensional sphere like depicted here. And qubits in different states are just going to point in different directions around that sphere. And we can change from one state to another by rotating that sphere. So the first example program that I'm going to show you is a very basic like hello world type of program for one qubit, but it covers a lot of the syntax that you'll need to get started with Cuda Q. And our program is going to take a qubit in the state 0, which is pointing up here, and we're just going to rotate the sphere 180 degrees around the x-axis and bit flip it. So change a 0 state to a 1 state. That's the program that we're going to start with. But if you're new to quantum computing, you might think, what is a quantum program? We can sort of think about a quantum program as having 3 components. The first is to initialize the qubits, and each row here represents a different qubit. So this would be a picture of a 3-qubit program. Then we need to manipulate those qubits. They're kind of storing information, and we're manipulating that information with gates that perform operations either on 1 qubit, like a rotation of that sphere that we just saw, or to entangle a couple of qubits with gates that operate on multiple qubits. And then the final state of the quantum program is to, or the final step of the quantum program is to measure the qubits to extract some information out of those when we execute that program. So let's just walk through the basics of how you program in Cuda Q. It is a C++ or a Python language option for you to program. I'll just demonstrate this one here in Python. And so a quantum program can be thought of as, at the most basic level, as a function that we are decorating with the @cudaQ.kernel. So you write a function just as you would in Python. We're defining a bit flip function. We want this program, like I said, it's going to be 1 qubit that we're going to flip from 0 to 1. So the first thing we have to do is initialize that qubit with the Cuda.Q vector. And this argument of 1 indicates that we're just going to have 1 qubit in our program. You could change that to 2 or 3 or 100 if you wanted. And then the next step is to manipulate it. But I'm just going to do this step by step to make sure that we have because my typing skills are, there we go. We first want to import the Cuda Q library, right? It's already done, but I wanted to make that call out that was implicit in this notebook. So we've defined this function. And so let's just see if we've actually defined a function that does initialize a qubit in the 0 state. So I'll just go ahead and use the add to block sphere and the get state functionality of Cuda Q to graph that qubit, and we do see that we have defined a qubit in the 0 state. And so now we want to flip it. So after we've initialized the qubit, we're going to apply an X gate. The X gate just rotates that qubit along the block sphere 180 degrees. So I've fixed my function there to do the bit flip. And then we can go ahead and graph the results of that qubit. And we see that we have changed the state of the qubit from 0 to 1. That's kind of like the most basic type of program that you'd write. And if you think about doing this with multiple qubits, you're not going to be visualizing all the qubits individually. And in fact, when you deal with entanglement, this notion of the block sphere sort of breaks down. So what we do instead is when we're writing a program for a quantum algorithm, we are going to do a couple of things. The first thing is that we are going to have to define how we're going to run that quantum program. And we do that with the set target command. And there are several different targets we can choose. We can choose a CPU, GPUs, multiple different quantum processors that we might have available. And the nice thing about that is once you've got your quantum algorithm written up, you can execute it on all these devices by just changing that target. So here we would be running it on a CPU if we use the QPP minus CPU. If I wanted to change it to a GPU, I would just change it to NVIDIA. So we want to define a function. This one will define a quantum circuit that does a little bit more. We'll have a quantum circuit on 2 qubits. So just like functions in Python, they can take arguments. The only difference is that our quantum functions here, our quantum kernels, have to take our arguments and have them the type be explicitly given. So here we're inputting the qubit count to say that we want to define a kernel with a certain number of qubits. We initialize those qubits with the Q vector, just like we did earlier in the previous example. And we apply some gates to those qubits. This being based in Python, we can use functionality from Python, like the for loops here, to simplify things down. So we can apply the gates. And then we take a measurement as a final step. Implicitly, if we don't specify it, the measurement's going to be done in the Z basis. Otherwise, we can specify different types of basises. once we define that kernel, we can then draw the circuit diagram out. So you can see here that we have a 2-qubit circuit, and we are applying a Hadamard gate to put the first qubit in superposition, and then the control knot to entangle the 2 qubits. And as the final step, we are going to sample the kernel, which the kernel takes as input the qubit count, and we're going to sample it 1,000 times. So we're going to execute that kernel 1,000 times, and within those 1,000 shots, we see roughly 50% of the time we read out the 0-0 state, and 50% of the time the qubits Q0 and Q1 are read out in the 1-1 state. So sampling is one of the ways that we can execute quantum circuits. Another common way of executing quantum circuits is with the observe command. And what that does is it computes the expectation value of a Hamiltonian. So we can define our Hamiltonian using the Cuda Q spin operators. In this example here, we just have the Z, Y, and X spins there applied to the 0 or the first qubit, respectively. And we're going to observe the expectation value of our kernel applied to the qubits with that Hamiltonian, and extract out the expectation value. And so in this case here, we get 0. And then the final way that you can execute the kernel is with the get state command, which will extract the probability amplitudes of the final state of the qubit. As we saw in this previous qubits, in this previous sampling, we saw 50% of the time we read out 0-0 and 50% of the time we read out 1-1. So the coefficients in the bracket notation of this quantum state would be 1 over the square root of 2 and 1 over the square root of 2, or 1 over the square root of 50%, 1 over the square root of 50, or I'm sorry, the square root of 50%, the square root of 50%, which we see as the coefficients here, 0.707 and 0.707, when we just extract those probability amplitudes out. So just depending on what you're trying to do and what in your program, you may use one of these 3 execution models. And in addition to being able to input the number of qubits into the function or the kernel, you can also create parameterized kernels or parameterized circuits by adding an argument for parameters there, float values of theta, and run your sampling or expectation value computations similarly. So that's a really quick run through of the basics of Cuda Q syntax. And I think now this is the end of our presentation that we had planned, and we're opening it up to Q&A at this point. So hopefully you got a little bit out of this. Think about what you've learned. If there's something you're curious to learn more about, or even how to get started, just let us know. We can answer those questions now.
And just encouraging you all, please don't be shy. We're more than happy to go through anything that's on your mind. So even if there's just a topic that you'd like to learn more about, feel free to put it in the comments. Thank you. All right, so our first one, exciting topic. Curious how Cuda Q is bridging the gap between classical and quantum workflows. And we did go through some real world demos, but of course we could always talk about more case studies and real world demos as well. But just throwing that over to the team.
Yeah, so I think one very obvious use of using classical and quantum workflows is actually quantum error correction. So this is the process of detecting and correcting errors as they occur in real time, and is kind of one of the key things to unlock useful quantum computing in the future. So the process of actually detecting and figuring out what is the real error that occurred on the quantum processor is a classical process and needs some real-time compute, and is actually a non-trivial classical compute question. So that is actually one very concrete workflow that will require the tight integration of classical and quantum workflows. That's something that we're building towards. But there's also applications where much of the computation actually will want to happen on a classical supercomputer, and then portions of it will be passed to a quantum computer. So one example of this is recent work that we had with AstraZeneca, IonQ, and AWS. And this is a process where we were simulating a molecular kind of quantum chemistry problem, where parts of the problem were run on the quantum processor, and then the results of that were fed to a pretty massive GPU cluster for post-processing. So this is something like 40,000 GPU hours used to post-process those results. So another example of kind of a quantum chemistry workflow that really is is required to use a large amount of GPU compute alongside a quantum processor.
All right. How do we know the qubit is in both 0 and 1? The superposition. I'm assuming that this is I'm just going to throw this out. Let's see what you have to say about superpositions.
I can take a stab at this, and then if anyone else wants to add their own color to it. So basically, in an experiment, you're measuring the qubit, and you have to measure it in a certain so-called measurement basis. And so when a qubit is in the superposition, you'll measure a probability distribution where the qubit is in either the 1 state 50% of the time and the 0 state 50% of the time. But there's other measurements that you can do. For example, if you rotate it back into one of these basis states, you'll get the qubit in either the 0 or the 1 with 100% of the probability. So what that means is if you rotate it back into the basis state from the superposition state, you kind of understand that the qubit was truly in the superposition state before from the probability distribution.
Yeah, and Zach, if you could pull up my screen again, I can just show an example of that a most basic superposition. And if you want to learn more about this topic too, we have some notebooks on Cuda Q Academic called The Quick Start to Quantum, and the first notebook actually walks through more details of exactly what Jinsung mentioned with the different basis measurements. But this is an example here. I've just taken our previous code and edited it a little bit, where we have 1 qubit, and we are applying the Hadamard gate, and the Hadamard gate will take a state that was originally in the 0 state, which is how all of the qubits are initialized in Cuda Q, and transforms it into a state of equal superposition or along the x-axis of that black sphere.